Hey guys, welcome to video learning. We're going to do 6.2 today. This is going to be as painless as possible, and 6.2 is actually a fairly easy lesson. So hopefully this will be nice and short and painless. We're going to learn dot product, angle between vectors, and projection of one vector onto each other today. There's going to be a couple times I'm going to ask you to pause the video to do something on your own. And then I'll just give you a countdown like 3, 2, 1, and then we'll just go again so that we're not waiting on you to do the computations. Although I hope that you do them along with me and don't just write down what I'm writing down. It'll make a lot more sense to you that way. Okay, so here is your warm-up. This would be a POD if we were actually in class, but we're not. So we're just calling it a warm-up. And I would like for you to find those 3 items and label each as in what vocabulary word describes the little up and down lines on each one of them. So go ahead and do that and then pause the video. We'll start in 3, 2, 1. Okay, so you've done this hopefully now. The first one, the answer is 4, and that's called absolute value. And that's the one that you've known for a long time, and that's when you're looking at a real number. And that represents the distance from 0 on a number line. So if this is 0 and this is -4, that the distance from 0 on a number line is 4. The next one is called modulus. And we did this when we were learning complex numbers. And the modulus of a complex number is its distance from 0 on an argand diagram. So 0 is the origin. And this is the real axis, and this is the imaginary axis. And so 3 plus 2i would be this point right here. And then when we find the distance from the origin, that would be the Pythagorean theorem. 3 squared plus 2 squared square root, I get root 13. And that would be the modulus of that number. And then the last one is the one that we just did. And that would be the magnitude. And that's because what's inside that symbol now is a vector. And so here, it doesn't matter where you start, there's no origin necessarily, right? Vectors have magnitude and direction only. So for the magnitude one, we just start anywhere and we would go right 3 and up 2 and draw our vector. And the length or the magnitude of that vector would end up being root 13 as well, because these two would be the same length. Right? Although this one is just the distance from this point to this point, and this one we're actually looking, in the third one, we're actually looking at a vector. So the symbols are related in all 3 cases, but they have different names and they mean different things. Okay, so that was your warm up, and now you're ready for dot product. Here we go. So the formula for dot product, if you have 2 vectors, AB and CD, remember the word product means multiplication. So a dot product means that the symbol in between them is a dot. There's also a thing with vectors called a cross product where the symbol is the little x. So for those of you that still like using the little x, you cannot use the little x here because that means cross product, and that's a different thing that we're not learning. So we're just doing dot product. Notice that if I I'll call that vector u and this vector v, and then this is a dot. It looks just like a times dot. You can make it a little bit bigger if you want, but you don't have to. It really just looks like a times dot. So then the dot product of this would be that you would take the x components and multiply them, and you take the y components and multiply them, and then you add those up. Notice that u dot v results in a scalar, which is just a number, right? We did that in 6.1. So we have a vector and we're dotting it with another vector and we get something that's just a scalar. Go ahead and do this first example here. Pause the video. And I'll start in 3, 2, 1. Okay, hopefully you've done this. You did 3 times 5 plus 4 times 2, and you got 15 plus 8, which is 23. Pretty easy, right? Good. Why would we want to use the dot product? What's the purpose of doing that with 2 vectors, you ask? I'm so glad you asked. Turns out you can use a dot product to find the angle in between two vectors, which comes in really convenient. So the formula for the angle in between vectors is that the cosine of theta is going to equal u dot v over the magnitude of u times the magnitude of v. Notice here that I called this one a dot and I called this one a times, even though they're the same symbol, because the one on the top is with vectors and the one on the bottom is two magnitudes. So those are just two scalars. They're two numbers that we're just multiplying together. And so go ahead and do example 2, which is finding the angle between the vectors that we were just looking at on the last page. Pause the screen and we'll start in 3, 2, 1. Okay, here you go. So hopefully you said cosine theta equals u dot v, which we had already said is 3 times 5 plus 4 times 2. I'll write it again anyways, which was 23, over the magnitude of the first vector, which that would just be a 3, 4, 5 Pythagorean triple, and then times the magnitude of the second vector, which do the x component squared plus the y component squared square root, and that would be root 29. So we get that cosine theta is 23 divided by 5 root 29. And we're not going to worry about rationalizing that because we don't care about that number. That number is not our final answer. We want to know what theta is. So go ahead and make sure your calculator is on degree mode and then type that into your calculator. And I believe that you get that theta is 31.329 degrees approximately. You can check your work then by just drawing the vectors and looking at it. So the vector 3, 4, if I go right 3 and up 4 and draw that vector, and then I'll go right 5 and up 2. Notice I'm not adding the vector, so I'm not going from the tail of one to the head of the other or the head of one to the tail of the other. I'm starting them at the same vertex because I'm finding the angle in between them. And so then this would be theta. And yes, that looks like about 31.329 degrees. All right, next. Here's another example for you. Find the angle in between those two vectors. Pause the screen and do that. 3, 2, 1. All right, so hopefully you started off by saying cosine theta equals u dot v. So that would be 2 times 10 plus negative 5 times 4, which is also 20, but negative. And you'd get that that's 0 over something. And then at that point, if you were smart, you wouldn't have even calculated the magnitudes of the bottom because you know that 0 divided by anything is okay, and that answer is 0. If you did calculate them, you can check to see that you calculated them correctly. That one would be root 29, and this one would be root 116. So this would be whatever 29 times 116 is, square root of that. But it doesn't matter because we're going to get that the cosine of theta equals 0. And you can type that in your calculator if you like, but hopefully you don't need to type that in your calculator because you know from the unit circle that if we look at the unit circle and say where does theta equal 0, that would, or cosine theta equals 0, that would be right there at the top where theta is 90 degrees, which means that these two vectors are perpendicular. However, if we have vectors and not just lines or line segments, now we have a new fancy word for perpendicular, and that word is orthogonal. If we were in class, I would implore you to please, please, please pronounce it correctly, that this is orthogonal, not orthogonal or something like that. So we want to sound as intelligent as we actually are. Please pronounce it that correctly. Orthogonal vectors just mean two vectors that are perpendicular. Okay. This actually gives us a little bit more information then. If we look at that formula and we say that cosine theta equals u dot v over the magnitude of u times the magnitude of v. And if I multiply both sides by that and I get the magnitude of u times the magnitude of v over here, I get this other formula, right? Same formula, but in a different form for the cosine and for the dot product. And notice that these magnitudes are always positive. So I can actually just look at the sign of the dot product, and that'll tell me some information about the angle. If u dot v is positive, then that must mean the cosine of theta is positive, which means we're looking for positive x values, which means that theta is acute. If cosine of theta, or if u dot v is 0, we already said that that means that theta is 90 degrees and that those are orthogonal vectors. And then last but not least, if u dot v is less than 0, or negative, right, then we're looking for a negative cosine value. So cosine theta would be negative, which means that theta is obtuse. Notice I'm only looking at the minor angle. So for any two vectors, they're going to create a major and a minor angle. Minor means less than 180 degrees. So this would be the theta that we're talking about when we use the formula, not the one that's greater than 180. Even if the angle is obtuse, okay, fine, but this is the theta that we're talking about, which is the minor angle, and we're not talking about the major angle. We're talking about the minor angle there. So the choices are 0 to 90, 90, or 90 to 1. Okay, last but not least, I hope you're hanging in there. Our last topic is the projection of u onto v. And this looks complicated and it's actually not, so don't freak out. If I take two vectors, I'll call this one vector u, and that's the vector 1, 2. And then I'm going to make another vector, and I'll call it vector v, and I made that vector vector 3, 2. The projection of u onto v, which just means the component of vector u is in the direction of vector v. So if I break vector u up into two vectors that are perpendicular to each other, but one of them is in the direction of v, that's the projection. So to do that, I'm going to put my pen on the end of the tip of the arrow, and I'm going to drop a perpendicular down to vector v, and then wherever that perpendicular meets vector v, right there, that is the projection of u. So notice u is the one that's normal size, that's in the line, and then onto v, we go backwards and we put the little subscript in of onto v after that. And that's how you would read that. And let's go ahead and do this example. Notice all of this is just a scalar, right? It's just u dot v results in a scalar, and then magnitude of v squared is a scalar. And you could also write that as u dot v divided by v dot v, which I actually like, as in it's more consistent with the formatting of it, times vector v. So u dot v in this case would be 1 times 3 plus 2 times 2. And v dot v would be 3 times 3 plus 2 times 2, which is just the component of the magnitude, like you're doing a squared plus b squared, but then you're not taking the square root of that. And so that would equal, what, 7/13? And then, so that's the scalar component, or the scalar factor that we need to multiply vector v by. So turns out in this case, I'd have 7/13 times vector v, which was 3, 2. And then that would be the projection of u onto v in this case. If I go ahead and multiply that out, I get sorry, 7/13. I would get 21/13 and then 14/13. And then I can check by coming back over to my picture and looking to see if that makes sense. 21/13 would be like what, in between 1 and 2, 1 and a bit, and then 14/13 is just a tiny bit over 1. So that's saying I'm going 1 and something and then a tiny bit over 1, and I'm landing about right there. Obviously my picture was not perfect. I didn't even use straight line tool, but you can see that, yep, that's about where we landed. And so this blue vector right there, that was the projection of u. The last just note that I want to point out to you is that you can find both of them, so be careful about which one you're finding. The projection of u onto v means I'm going to drop the perpendicular from the tip of u to v, and then this would be the projection of u onto v right there, the black vector. But the projection of v onto u would be, I'm going to start at the tip of v and then I have to drop a perpendicular to u, which you can see that this is actually not going to be as easy as it sounds, because v is, even the u component of v is longer than vector u. So I actually am going to just extend vector u so that I can look at the picture better, and then I'm going to drop where the perpendicular would fall. And so it turns out the projection of v onto u would be this black vector here, which just means that the scalar multiple that you get is going to be bigger than 1, that u dot v is going to be bigger than v dot v, and so then the scalar that you get is bigger than 1. And that's fine. It doesn't really matter. Turns out the uses for projection, a lot of times you can use the examples that we normally do are for work. Work is force times distance, or force, the component of the force applied in the direction that the object is being moved. So we would do questions about work and moving a vacuum cleaner, etc. But we're not going to do the work problems this year. We're going to just forego those. So look at that. You're done with 6.2. So now go do your 6.2 homework, which is on my math lab, and have fun. And thank you for hanging in there with this video.